Зачем? На самокате удобно. Да масло смазал, колеса.
Дорогие друзья, dear colleagues, let me introduce Barnier from Institute of Geosciences, Barnier, Grenoble, also head of Mega Grant Lab at PP Sharshov Institute, Russian Academy of Science. This year, the first year of your contribution to our Mega Grant program. So, please, если я не ошибаюсь, Бернар просит до часу и просит, если задавать вопросы, это можно делать прямо в течение его доклада. So, please.
Thank you. Good afternoon to everyone. It's my great pleasure to be here and to have a chance to present the work, some of the work we've been doing related to computational sciences. And I hope I will show you computer science is really at the heart of the oceanography, modern oceanography at present, and it's very, very important for us and for our research. So the top of my presentation is stakes and frontiers for global ocean modeling in climate and operational systems. Rather than stakes, I should have used the word challenges. My presentation will set the context of the mega grant, which I'm going to work on in the next 3 years at the Sharshov Institute. Below, I put all the project and various organisms in France who have been supporting the research, which I'm going to present now. So first, some acknowledgement to some good people in our group in IGE. Jean-Marc Molly, Thierry Pendif, and Julien Le Saubert. This guy will visit IRAS, Sharshov Institute in July, and this one will come in June this year. Part of interaction between the two labs that we are beginning to build up with Sergei. And part of the work I'm going to present has been produced by these colleagues. I also want to mention the Hubert Curien-Kolmogorov program, which is a cooperation program which is funded by France and Russia between IG and IRAS. So it's a limited funding for traveling, but it's very useful to exchange a student and scientist. And also, of course, the mega grant from the Ministry of Education and Science of the Russian Federation, which I'm going to carry on with in interaction with Professor Sergei Gulev, who couldn't be here today. He's traveling, I think, in Taiwan for some reason. So the outlines of my presentation. I got 3 big parts and one which is a bit shorter because this is just beginning, so I don't have much to tell about. I will first, because mention a little bit something about the usefulness of numerical models in ocean sciences. Then I will present 2 emerging questions in oceanography. And I present those questions because they are related and we can address them with computational challenges. So one is the impact of the small-scale dynamics of the global circulation. I will explain a bit what this is. And which requires a challenge by modeling the ocean at kilometer scale. Another one is the intrinsic and chaotic low-frequency variability of the ocean circulation, which addresses big issues in climate. And which requires development of new ensemble simulation approach, which are also very demanding in terms of computing. And then I will tell a bit more about the mega grant and how it relates to those challenges, and how important are computer sciences for the project. So first, numerical model in ocean science. So the numerical model now are a pillar of oceanography, at least that's my view of it, as important as observation, in situ observation, and satellite observation. If we take the best program that we have at the moment, which is the Argo array of profiling floats. So for those who are not from oceanography side, we are at present, almost 4,000 profiling float in the ocean. A profiling float is something that drifts at 1,000 meters, and every 10 days goes down to 2,000 meters and goes up to the surface, making measurement and sending this measurement at the satellite on the surface, and then it's going down. So those floats are the best network of observation that we ever had in oceanography, but still yet, if you look just the Gulf of Mexico, you have 10 to 15 floats in there. With 15 floats, you cannot sample a turbulent ocean. So in situ observation, they do not sampling is sparse in space and time to observe the full ocean, the full turbulent ocean. Then we have satellite observation. So satellite observation, satellite goes very fast around the world, and they make measurements, so they can give some kind of an instantaneous view of the ocean, but they only make measurement at the surface. They don't go into the deep ocean. So you get information from the surface, which is also integrated when you compare to a measurement of a float. This is very local measurement, while a satellite is an imprint of 10 or 50 kilometers on the surface. So it's a bit different nature. So the satellite has a good sampling, but it's only limited to the surface. So therefore, we don't have a 4D time and space sampling of the eddy field, which is the weather of the ocean. Is not sampled by observation. So that's where a model enter into play, because dynamical ocean model there can be used to link the surface from satellite and the deep observation from in situ through dynamical process, because a model is solving the equation that represent physical processes, and from that you can, with different type of observation, make the link between those using a model. Okay, so they're used to integrate observation of different nature into a coherent dynamical system, like very point-wise in situ measurement and surface area integrated satellite observation. So this model are needed to understand and interpret observation. They are also, of course, important for climate projection and operational analysis forecast. You need a model to do a forecast, of course, and those models are used for that. So now, at present, I think that ocean models are as important as observation from satellite and from in situ measurement. So, but choosing a model, what does it mean? And using the resolution of a model, the grid resolution, it means choosing the scale you want to resolve. It's not just, you don't say, well, I have a great amount of memory, so this is the grid, in this domain, this is the grid I'm going to choose. That's not the way you do it. The way you do it, you say, what are the scales I want to resolve? So if you were thinking of the weather of the ocean, which are the synoptic scale of the ocean, the characteristic scale of the weather, ocean weather, which we call the eddy scale, is this line. That's the zonal average. This is longitude, latitude. The zonal average of that scale is given here, and here we have the scale in kilometers log scale, 1,110 line. Okay, and this is a minimum value in the zonal average, and that's a maximum value from that scale. And those lines are the resolution in part of the portion of degrees from different models, 1/2 degree, 1/4 degree. And this one is IPCC model, the model that do climate projection at the moment. This is the resolution is higher than this one, or equal to that. So you see that they don't resolve the weather scale. So if you ask a meteorologist, I want to do climate projection, but I'm not resolving the synoptic perturbation, you're not going to believe that the model is going to be any useful for that. So that's the case of the ocean. So we'll see it's a bit different for the ocean. So we ran, those are the various resolutions. You see from 1/4 degree and 1/12 degree, which are the model which I'm going to talk about it today. We can resolve the scale, you know, from the 1/4 degree, about 50 degrees is north and south. And for the 1/12 degree, we basically resolve the weather scale almost everywhere. So just to show an example, not immediately, but I'll tell you. Just to show an example, here I show anomalies of the sea surface elevation, which is related, of course, to ocean current. So the sea surface elevation of the ocean. This panel is the one obtained, it's a snapshot, you know, on 6 January 1993. This one obtained for the satellite observation from 1993. And here we have 3 models. 2-degree model, 200 kilometer resolution. 1/4 degree model, 25 kilometer here and 10 kilometer there. And the 1/12 degree, which is used for operational forecasting, is 9 kilometer and 3-4 kilometers below latitude. Okay? So what we see here, the first look is that the large scale, if the coarse resolution model, you know, is captured by that model. So the model used in IPCC have skills, which is very reassuring because we have a lot of you know, in IPCC report information about climate change, and those models have skills. They have skills at the large scale, which is the climate scale, which is very interesting and very reassuring. And when we increase resolution from 1/4 degree to 1/12 degree, then we get picture, the instant snapshot picture begins to resemble very much the one observation. So those models, you increase the scales to all the smaller scale when you increase resolution, which is very interesting. So you can show the movie now. So we're doing animate. So you can see that the phase, the very large scale phase is remaining in phase with the, okay, you can just stop it at any time, okay, pretty good. And you can see that we're still getting the phase, you know, after a different period for the coarse resolution model, but those models are getting closer to the real observation. So the model have scale at all resolution, but we'll see that there are some drawback with this model in terms of variability. So, so now let's go to the energy question that I want to talk about. So the impact of the small-scale dynamics on the global ocean circulation. So this is related to...
I'm sorry. Small-scale means sub-scale processes.
No.
Resolvable.
Resolvable, but small compared to what we call I would make this different, like you have a laminar flow or you have a turbulent flow. So the large scale is the laminar flow, would be laminar flow, and the small scale will be when you resolve turbulence, so turbulent flow. And then we have the subgrid scale for the molecular cells that are not resolved by the flow. Okay, so it's a good question. We need to make this clear at the beginning of the talk because it's very important all along. Future observation from space. So this is Julien Le Sommer from the group who will be visiting in June. Is very much involved in that. You know, if you look at present what we get from satellite observation in terms of resolution, for the sea surface temperature radiometers, we can get 2 kilometer resolution when there is no clouds. Of course, at passive microwave that works even when there are clouds, we don't get better than 25 kilometer resolution from observation. The sea surface elevation, which is connected to surface pressure and surface current in oceanography, at present, you know, radar altimetry, which measures at the nadir, which if you have a satellite, it's just a line like this, you know, resolve about 100 kilometer resolution. But there is a future mission, SWOT, which is being prepared by the French Space Agency CNRS and by NASA, which should be launched in 2020, but it will be probably 1 or 2 years later, delayed. This is going to measure the sea surface elevation in a range from 10 to 100 kilometers, and it will be one thrust, 2 thrusts with a resolution of 10 kilometers within this, plus a Barnier. So the resolution is going to increase significantly, and in fact, if you consider that this is an ensemble ocean spectra of different variables, you know, this is the noise of the present JSON observed satellites, so we cannot resolve all this part of the spectrum. This is the next generation of JSON satellites, JSON CS, which should be launched this year or something like that. We're going to get that part of the spectrum, and the SWOT non-spectrum will be at that level. So this is a 10 kilometer scale. So we'll get this part of the spectrum. So a really large increase in resolution. So if I go back to those two pictures, you know, I can say that this picture will not change. In beyond 2020, this will not change. We won't have more floats. You know, eventually 100 more. The risk is that we'll have less floats because agency will not eventually continue to fund it as the way it is. But this is not going to change. What will change of that is the variables. We get more variables. Right now we get temperature, salinity, few floats give oxygen or fluorescence, but we'll have more variables from those floats, but not more floats. So the sampling is going to increase from in situ observation. But on satellite, you know, that is going to increase by at least a factor of 10 in density and volume of observation. So the sampling discrepancy between this type of observation is going to increase very significantly. And this is, if we want to be able to use jointly those two types of observation, we need, you know, to make them match in some sense. And that's where we need to understand this very high resolution signal and to be able to see how it imprints all the observation. So this is a problem that we're going to solve. And therefore, the challenge for the ocean small-scale dynamics is we have to know what is the signature of those small-scale dynamics in the observation, and especially in the situ observation, because it is in the observation, but we cannot separate it or identify it. And also, we need to know what are the key impact of the small scale on the larger scales. And for that, we need large-scale model, because if you want to know if your small scale impact the large scale, you need to have the large scale in your model. So there is the key ingredient to solve this is resolve very well the lateral gradient and the surface stratification, and to resolve the mesoscale and
what do you mean surface stratification?
Why?
What is surface stratification?
Well, stratification is in the upper ocean to have resolve very well the density gradients.
Upper layer of ocean.
Yeah.
Not surface.
Upper ocean. Okay, yeah. The surface, you may think of
Surface layer.
Yeah, the surface layer. So the modeling and computational challenge for that is to resolve the small scale in large scale basis, which means large domain, high resolution. And for that, it's very clear, considering the dynamic of the small scale, that we should aim at a resolution of the order of 1 kilometer for a large domain. So I'll come back then to this numerical challenge. And now I'm going to the second emerging question, which is intrinsic and chaotic variability of the ocean. So this result has been coming from Grenoble. Aiding ocean models, a model that resolve the turbulence, you know, they allow to quantify for the first time the intrinsic low frequency variability of the ocean. We had no idea of what it was before. The model could tackle this issue. And how we did that? So I'm going to explain a little bit these things. You know, a model, you have initial condition, which is temperature and salinity of the ocean as historical data that is put in a global model. And we have atmospheric forcing, atmospheric condition that is driving the circulation on the top. So one is a full interannual forcing, 50 years of atmospheric reanalysis. So we have interannual variability, we have 6-hour variability, daily, monthly, things like that. Okay? And then we construct from that a forcing, which is only a climatological seasonal cycle. So it has no interannual variability. Every year, it's exactly the same seasonal cycle that we apply to the model. So we have one model which is driven by fully by a full atmosphere, which has all the variability of the last 50, 60 years, and another one that has absolutely no interannual variability, just a seasonal cycle repeat. We tried a 2-degree ocean model, a 1/4 degree ocean model, and a 1/12 degree ocean model with those two forcing and same initial condition. So we have the results. We have 50 years of simulation. And then we extract from that the low frequency signal, which is period longer than 18 months, by detraining and bypass filtering. And therefore we have the low frequency ocean evolution, which is purely intrinsic, which we call purely intrinsic because it's a low frequency, but there were no low frequency forcing in forcing, atmospheric forcing, so it is generated by the ocean. That's why we call it intrinsic, generated by the ocean. And you have the full one, which has the one that is injected by the atmosphere into the ocean, and the one that the ocean also generates. And so if you look at the measure of this intrinsic variability by the variance of this simulation and the variance of that one, and you make the ratio, and you multiply by 100, you have what we call the ratio of the intrinsic to total. Okay? So just to illustrate this, I have here a motion picture that we first look at before it starts. These are observations of sea surface elevation from satellite. This is the model full interannual forcing. Okay, so this picture is interesting to verify that the model is doing a good job. You know, and what you can see that those snapshots, those features, okay, are well represented. You have so many features which are not in the model because it's only a 1/4 degree, but you will find in 1/12 degree. But you still do see the turbulence. So the model is doing a good job right there in simulating observation. And this is the intrinsic simulation. And you see that there are differences between the two. Now you can start the movie. Okay, so when you see the movie, you can see that the big events are reproduced, so that we can trust this model. And when we compare that one and that one, we can see that in the tropical ocean, intrinsic variability is very weak, which means that basically there the ocean responds to the atmosphere, doesn't generate its own variability. But in this region, that region, and this region, then it's very clear that the intrinsic variability is as large as the one that is driven by the atmosphere. And that's the first time that we could see and measure this kind of thing was coming from any resolving model. If you do the same thing, we'll change it. If you do the same thing with a 2-degree model, okay, the upper panel is blank. There is nothing. So the 2-degree model, the coarse resolution, the laminar model, doesn't generate interannual variability. It responds well to the atmosphere, but doesn't add its own variability. So this ratio here, we plotted this ratio from the 1/4 degree model on this map, and what you can spot the sea surface elevation, and you can see that there are regions like those one where the intrinsic, this ratio is 100%. So all the variability there is driven by the ocean. The ocean generates it. Okay? When it's blue, it's fully forced by the atmosphere, and as soon as it starts yellow to red, it is 50 to 100% due to the ocean itself. So that's a new paradigm to interpret observation. And if we look at more integrated property and climate indexes, like the meridional overturning circulation, meridional circulation, which is heat transport to high latitude and to low latitude. So we plotted this, the volume transport associated with this overturning cell. We plot this ratio for this circulation, a function of latitude. The 2 degrees is the red line, no variable interval, so intrinsic is 0. But at 1/4 degree and 1/12 degree, then you see that it is between 20 and 30%. So 20 or 30% of the meridional variability, low frequency variability of the meridional heat transport could be is driven by the ocean, and that will impact, of course, on the climate variability. So that is completely off present IPCC projection, but it will probably come into in the future because they are going to use this type of model for the projection. So looking at the intrinsic variability, we found that it is sensitive to small variation, which means it's chaotic, and it coexists with the atmospheric force. It's hard to separate them, which is, this one is being deterministic because it responds to the atmosphere. And if we want to separate those two and look at them independently, and when it's chaotic, then the only good way is to start with a probabilistic approach and to run ensembles. Okay? So instead of doing this experiment by doing one, we should vary the initial condition with a full annual forcing, and with forget about that one, we just all with ensemble, we could get to study the chaotic and the deterministic part. But this is a very big computational challenge, which we have to address. So now I'm going to the third part of my presentation, and I will discuss the numerical modeling and computing challenge which are associated with those two, starting from the small scale dynamic and the 1 kilometer model. So how do we address this issue? So just going back to this figure, 1 kilometer is here. So we do resolve pretty well. We have a large number of points to resolve this dynamics, the weathers here. So that's where we go. So of course, before I go into details, I will just a few words about the ocean model that we're using. So we're using the numerical code which we're using is NEMO, Nucleus for European Modeling of the Ocean. So it's a model that anybody can download from its website and use. It's free to use. It's a primitive equation model, which means there are some approximation to the Navier-Stokes equation. The model is hydrostatic, Boussinesq equation, some others, but it is a realistic setting, which means realistic coastline, forcing, stratification, initial condition coming from observation, and so on. In practice, what we solve is the evolution equation of the variable that describe the physical state of the ocean, including the sea ice, because the sea ice is just the ocean that freezes, so it has to be taken into account. Okay? The model is developed by 6 European institutions. CNRS as the lead. Mercator Ocean with the operational system in France contributes. Then the National Oceanography Center in Southampton, the UK Met Office, and 2 institutions in CMCC, the Climate Center in Italy, and the INGV in Bologna in Italy. It's used by more than 1,000 group, and including 8 Earth system models who are doing the CNIP6 experiment. And of course, it is also the model that is used by the Copernicus Marine Services to do operational forecast. Okay? But there is also the hierarchy of global model configuration, which is developed and implemented and maintained by European coordination, which we name BRACA, from the name of the writing ship, which we led in Grenoble. And we group a large number of institutions who are using global configuration, and the hierarchy goes resolution from 2 degrees to 112 degrees. So 1 degree, half degree, quarter degree, so we have all hierarchy of resolution for this one. So now we're going to go to the kilometer scale, and we started to apply this to the North Atlantic, because it's a very big domain, and we're going to see it's already a challenge. So this model configuration is North Atlantic 160, so N for North, 88 Atlantic, 60 for 160. So that's the name of the configuration. So you're using NEMO version 2.5. The horizontal grid is 160 degree, 1.6 kilometer, and 800 meters over there. It's a Mercator grid. 300 vertical levels, 1 meter at the surface, 200 meters at the spot of the basin. Almost 5.7 billion grid points. We run the model for the objective of 5 years. Initial conditions are coming from ocean reanalysis, and the forcing is a realistic forcing that is derived from the BRACA project.
I am sorry, but still hydrostatic approximation.
Yes.
In this version.
Yes.
Why?
Forcing. Why? The non-hydrostatic version of NEMO doesn't exist yet. So an answer, but can be not satisfactory. For the processes we're looking at, and the small scale we're looking at, from what we experience, we don't need the non-hydrostatic model as long as the parameterization that we have non-hydrostatic models, processes are doing, and this is still an open question. I'm not sure they do. Okay, it's still an open question. So this is an issue of that resolution. We begin to be to a resolution where we should have an evolutive prognostic equation for the value of the vertical velocity, which we don't have in hydrostatic models. We should probably have it at that resolution. And so the model, so this is a topography of the model. This is a zoom of the grid. So it's a 3 point. So we ran this on the Oxygen computer, which was a new computer at the National Computer Center in Montpellier. So the machine is a blue machine, which is a 2.1 petaflop. So we ran this 2 years ago. 21 petaflop, and we got 17 million hours of CPU time to do this simulation as testing the machine. The idea was we need a hard test for that machine. So what do you propose? We proposed that, and we were selected with a few other groups. We test the machine, and so we got the computer time to do this simulation. So how do we do that? So we cut the domain in 13,000, the whole domain in subdomains, 13,000 of them. Okay, so if we zoom a little bit on that, those are all the subdomains. One subdomain has this type number of points, and there is 1 point overlap. So 1 point overlap means that we don't do the overlap point I computed twice. Okay, so this is a loss of time. But by having only one point overlap, this is the constraint on the numerical scheme we can use, because if you use a large stencil, it's not going to work at the boundaries. So if you want to use large stencil, you need to have greater overlap, and then it costs more. So we have a simple numerical scheme, centered scheme, second order, and so on. Okay. So, and of course, all domain on land, we don't need to calculate them, there's one way. For such a simulation, the output strategy is very important, because we're running the model, but we want to say from the first time step to the last time step. You know, we're looking at the evolution of the ocean. So we need to save the time evolution. So storage is very important. So for the storage, of course, for oceanographers, we've been looking at some regions where there are observations that could be used to validate the model. So we identify those, and this one is one, and this one is another one. Some other regions were interesting process and pure, where we set at a very high frequency, like daily means. You know, time step is I think, 60 seconds or something like that, but we're saving the elements. But we also set hourly values along sections, and otherwise we set the whole domain every 5 days. To do that, we have a dedicated process which is separated from the model itself, which requires a large number of cores. So for that simulation, it requires 286. So the total model is 13,000 for NIMO, 296 processors, cores for the IOs, which we call XIOS. So that was 26% of the whole machine for that small simulation. And of course, how did we get to this 13,000 cores? For that, we did what we call scalability test experiment. So what you do, you start a model, you say, okay, well, I'm going to make a run with 3,000 cores and see how many time steps I am doing in a minute. So the time step per minute is a counting unit, and you're looking at how many time steps. So with 3,000, we have two experiments, 20 or 30. So there is variability. You start, and it's a large variability. We had this problem because the machine was new. This problem after the machine improved and get a bit older and more controlled by the system, and controlled by the people running it. This shrunk a little bit. So the blue are similar tests, you know, and you see the model is very scalable. Okay, we increase the number of processors. Fine. But we then test with the XIOS, the IOs. Okay, and we found that there is a big sensitivity of the performance just with the XIOS model that does the IOs. With different IOs, you know, we were having large variability. We also found, and that was more amazing, variability according to how we pick the processors. You know, we have, can go back to this. Okay, and I have a processor, a domain here. So I say, well, I'm giving this domain a core. Okay, and this one I will give a core which is on the same node. Okay. And this one also on the same node, so since I have, I think, solution of 16 node per, 16 core per node, you know, you can make blocks, and you do that, and you think that you're going to go faster. That was not other way around. That was a disaster. That's the worst performance we had. So we wrote a software where we were randomly picking the neighbor, you know, with this processor. We should pick up randomly anywhere another processor, but exclude those we are justified. And that's where we get the best performance. But that is related to that specific bull machine. I think if you get another machine, it might be different. That's a way, or it's really in the hardware that things happen here. So that's why it's very important when you do this big frontier simulation that we work with the computer center. The computer center is a real partner. It's not just a service. It is a full partner of the project, because otherwise you will never find this kind of thing. You just say, well, you know, I get bad performance and why, and so on. Okay? So it's very important to have a partner. So at the end, we end up to pick up this 13,000 core. And if I look at the efficiency, so the efficiency is the theoretical, the effective speed up, the ratio of the effective speed up to the theoretical speed. We ran at 90%, which is pretty good. So we ran 18 million CPU hours on 13,000 cores for the model, plus the 300 cores for the IOs. We did 75 days of computation in 60 working days, which we running. The machine was really tested. We submitted 272 jobs in this integration windows. 100 terabytes of data were generated, reformatted and restored. Then, of course, we have a continuous feedback with the CNRS computer center, which really worked as a partner on this project. And that's why my first acknowledgement went to Jean-Marc Molin, because he's a guy who was able to make 57 days of computation on a new machine in 60 days, which means he slept on his 3 days in 2 months.
57 days for continuous work.
Yes. That's why it is more than and I hope you will have a chance to come and visit here. So, some results. Seasonal variation of the small scale. This is an important result that came out. We're not the first to produce that one, but more will illustrate it very well. So here I'm showing the relative vorticity, which is the vorticity of the current, you know, the dV/dx minus dV/dy, scaled by the colors parameter. This is a snapshot in winter, in the month of March. It's here, but the scale is minus 1 to plus 1. So you see the Gulf Stream, you see all the Gulf Stream rings, eddies, Erlanger rings. Then you see a lot of very small features in there. Okay? So if you zoom on this region, what we see here is big eddy. Those are what we call the mesoscale eddies, the weather of the atmosphere equivalent to atmospheric perturbation, much smaller scale inversion. And you see much smaller eddies and filament and things. This is what we call the sub-mesoscale eddies. Okay, so we have two scales there, the mesoscale and the sub-mesoscale. Beyond that, we don't resolve them at 1 kilometer. Okay? Then in summertime, it's much quieter. A lot of things just disappear, especially the mesoscale. So if you zoom in, what you see we see that the mesoscalides are very nice, very smooth, beautiful things, almost a theoretical. And there is some mesoscale that's still around. You see filament, some mesoscale. But the picture is very different. Although most of the sub-mesoscale is here. So in fact, those small scale LEDs, they have a seasonal signal. So we try to quantify what is the variability, the variance of this sub-mesoscale. So we try to calculate, estimate the sub-mesoscale variance. For that, we take a 1 degree box, calculate the spatial average of the vorticity, and then we call that parameter the time average variance. It's average over 1 month. The difference between the spatial average and the instantaneous value, so we take the square, and then we average that over a month. So if we do that, on every 1 by 1 degree boxes, we get the value for the parameter, which is when it's dark blue, which means high value, when it's white, it's low value. So we see already where we have variance. Okay, that was for the month of January, March, okay. But we have a seasonal signal of that variance. It peaks in winter and it's minimum at the end of summer, at the beginning of fall, and then it goes back in the winter time, and peak in March, in fact. So what we do is we calculate the normalized ratio of the maximum variance and minus the minimum variance. Okay, and that number, which you're looking at what it is, it tells you where the variance of the mesoscale is big. Describe the seasonal cycle. So we did that for the vorticity. That's a min-max ratio. It's big in this region, the Labrador Sea, Gulf Stream. It's a region, but we know this region where it's, like this pool here, where it's small, where basically there is little seasonal variability of the small scale. If we do the same test on the surface temperature, sea surface temperature, we get that now. Basically, no seasonal variability of the small scale variance. So which means that processes that create the small scale variance here is probably different on the SST are not those who create the small scale variance on the dynamical wire, which was surprise for us. So our conclusion on that, of course, this is on the it's on relative vorticity, strong seasonality of sub-mesoscale variance, also sub-mesoscale turbulence. Okay, and the maximum summer-winter differences are found in the superagile. But for the sea surface temperature, there is a weak seasonality of the small-scale variance. So the small-scale variance is probably resulting not from the small-scale anomalies, but from the strain induced by the larger scale, the mesoscale flows, and not directly related to the sub-mesoscale. So that is an important result for fluid mechanicists and people looking at ocean turbulence. So the last numerical challenge is ensemble simulation. So this is mainly the work from my colleague Thierry Pellu, who will see in July. So this is an occiput from the occiput project, Oceanic Chaos, Impact, Structure, Adaptability. The idea is that to understand what is atmospheric constraint on the turbulent ocean. And for that we set up a 50-year-long, 50-member ensemble simulation with global model that resolved it. So it's the first time that was planned. So we don't see the picture, but this should be an animation where you see all the models starting together, which is an ensemble. So the thing is, when you do an ensemble like that, the ensemble dispersion gives you the chaotic variability, and the ensemble mean gives you the force variability. It's schematic, and the statistician will have a lot of things to say on that, but that's the basic idea.
Excuse me, usually 140-degree resolution is called eddy permitting.
Yeah, it's eddy permitting. So that's why I'm using eddy motion.
Eddy resolution model. Yeah. Eddy means eddy resolution.
Means that you resolve, that you generate some eddies. It doesn't mean that you resolve all the. So we have some. So OCP project is carried on with 80 per million. As I showed on the first movie, the capture between 50, North 50 was the capture. They are able to generate a significant amount of variability. That's a good question. One thing we did is we verify, because we're also running 112-degree models, much higher resolution. Every time we have the eddy response, we try to verify if what the quarter-degree, the eddy permitting model is confirmed or not by the eddy resolving model in some sense. But we cannot run an ensemble at the moment of the global model. But if there are more questions after that, I can go on this. So the OCP project is the one. We want to run one quarter-degree model, so eddy permitting, which is a model that we can have on 120 cores. And we run 50 of them at the same time. Okay? So 50 global models that makes 5.5 billion root points. So as big as 1 kilometer North America. Okay? How we did it, I'll come back to this, is we first have a model spin up. Then we have to generate 50 different initial conditions. Okay? So we did that by doing 50 runs which start from the end of the spin-up. I'll explain to this one, which a perturbation in the equation of state, a random perturbation in the equation of state that generates 50 different initial conditions. And from that, we do 50 simulation from 1961 to 2015. So that makes more than 2,500, a lot of long years. Computed time was 20 million CPU hours. But this one, it was not on the same machine. It took us 8 months to do it. And we run on 7,000 cores, including 640 for the IOs. So of course, before we went to that setup, we did some tests. So the test we did is, on this one is interesting, you know, the color indicates the number of processor. Here you have the number of the members, and here you have time step by time per minute. So this is what we selected. So you see that when you increase the number of members, if this one is on 64 processor, it's very linear. So you can add as many as 20 members, 50 members, and so on. It's just a linear increase, and you keep the same performance in terms of time step. So all members advance as fast. The ensemble move as fast as only one. Okay, there is no overlap. The same for 128 shows, the same for the CL1. And you see that when you start to use 250 or 400, then you have some variability in the performance here. Here we plotted the efficiency, and for that configuration, the efficiency is above 100%, which is, we don't understand why, but we do better than the theoretical speed. So we set up with this one, and again, I'm not going to explain this thing, but you run 50 members, and you want to save all, or at least all the information that every model is generated. So the IOs is very important and very complicated. So this is a schematic of the IOs. It's very complicated. And one thing I want to mention is this one. What we do is, there are ocean database that are available where all observations made in the last 60 years in the ocean are available out there. So every member is generating an image of this database, which is a ensemble database. So we have 50 realization of ocean observation, of all of the oceans made by the model. Okay? And that's very important because for model assessment. So this will get, and also for altimetry. So we have the equivalent of all ocean observation over the last 50 years. But every time we have 50 model. So it's very complex, but it worked. So how did we generate the ensemble? As I said, we have a common spin-up. So one model is run, one member. In 1960 we stopped. Then we put a random stochastic perturbation on the equation of state. So we run 50 different runs with a different, with a random generation of noise in the equation of state, and that creates 50 different initial states after 1 year, 1961, and from that we continued with the same exact forcing to run all members. And at the beginning, then slowly the dispersion increases, and then we get to a thing where the dispersion is basically stabilized, and that's where the part that we're using for our study. What we did a double parallelization strategy, which means we have members and we have domains. So the regular way of parallelization is domain decomposition, but we wanted also to have each member could talk during the simulation with the other members. So we also add parallelization for each member. So we have double parallelization. This is up here in the recent paper, I think. So we have one MPI communicator for each subdomain, and we also have one communicator for each member. And so we can communicate in all directions. And this is very useful because it allows to have the PDF between the members calculated at every time step. And so we can do ensemble statistic online while we're running the model. And eventually, if you want to fit those things on during to one member or thing during a run, you can. So that opens a large, very interesting possibilities. So that's an example for the Gulf of Mexico, where the PDF of the sea surface elevation at the point in the Gulf of Mexico has a bimodal distribution, which is very amazing, but it's related to the separation of eddies from the curve. Okay, so when you run the model at the beginning, you know that the red one is satellite observation. The black one is the model, so the model is doing this. So it's a little bit shifted in time, but it's following at the beginning the satellite. And then we introduce the perturbation. This is the year one. So the stochastic perturbation is started from the same initial condition. The 50 members takes some time, but at the end, the stochastic perturbation on the equation of state, I created this ensemble, and then from that we start, and you see the dispersion is increasing. And at the end, when it's all dispersed, you see the ensemble model, really envelope completely the satellite observation. So all those are different realizations for what could happen in the Gulf of Mexico. So that's it. And of course, we need an assessment strategy which is different from what we did. So I'm not going to talk too much about that, but up to now we were running high-resolution model, but we saw 1 or 2 sensitivity experiments. Okay? So we look at the model in a deterministic way. But now we have an ensemble of 50 members. It's a very different paradigm because we can really look at in a probabilistic view. We just say the ocean is a chaos, or part of the ocean is a chaos, not completely, because there is something which is driven by the atmosphere. The ocean is a chaos, so we can have a very different approach to look at the ocean dynamics using a probabilistic approach, and that's very different things. And we're just beginning that. Something we're learning at the moment in the group in Grenoble, because it's something we just started to do 2 years ago. And so we're approaching statistician and meteorologists who have greater experience. I'm going to show a couple of results and then we'll finish on this one. The first result, the assessment of the decadal trend in oceanic content. That's very important, the trend in contents is global warming, okay, for climate. So, what we have 50 members, so we have 50 trends, and the ensemble mean of the trends, okay, which we plotted here for the heat content is between 0 and 700 meters. For the heat content, it's 700 and 2000 and 2000, 6,000 meters. So the color is positive trends in it's red, and bluish color are negative trends. So cooling of the ocean and warming of the ocean. So this is a trend due to the forcing of the atmosphere. It's one because it's the ensemble mean of the trend. How can I tell? This one you cannot get from observation because observation you cannot separate what is force from what is due to the ocean. How can I tell the significance of that? And for that, because we have an ensemble spread, then we can use the spread, you know, in a statistical test to test the significance of the trend that we have here. And that's what we did. We did tested the significance, identify significance level with the hypothesis of we have normally distributed random noise, you know, with zero mean, but the standard deviation is the ensemble spread. And from that test, then we could define that all H regions are regions where the 30-year trend cannot be unambiguously attributed to the atmospheric force. It could be an interannual, low-frequency internal variation just driven by the ocean. So that's an interesting result. I was just submitted, I think, a month ago, 2 months ago, by CNRS. And to continue on that, for climate things, we're looking again at Atlantic Meridional overturning cell at 35 degrees south, right here, where there will be an observational network in this region to monitor the overturning circulation there. So what is plotted here? Well, so we have the overturning, we remove the mean, we detrend for all members, and so we have the detrended with mean removed, so it's just the anomaly of the meridional overturning in million cube per second. Okay? So when it's a positive anomaly, you speed up the flow in this direction. When it's negative, you slow it down. Okay? So the black curve is the ensemble mean, so it is what is forced by the atmosphere. All the thin gray lines are every member, and the standard deviation plus or minus 1 is the big thing. Okay, so you can see that there can be significant deviation for members, you know, between members. And here, what is plotted is the variance of those time series. So the gray one is the variance of the spread. Basically, if you take the average, you know, over the whole this period, you will have a blue line. And this one is the variance of the black curve, and the variance of each individual have been plotted on those lines here. You see that there are some members have a variance of 0.8 compared to the variance of the ensemble mean of 0.3. But some members also have a variance which goes very, very small. Okay? And in fact, if you add the variance of this blue curve to this one, you get the total variance which is here. So the conclusion of that is that the variability of the meridional overturning circulation is 50% forced and 50% intrinsic at this latitude.
Is it possible to say that this variability is due to just trophic adjustment, or includes also the Ekman component?
I think we should be able to tell. We need to take the overturning circulation, all the members, and to cut it in pieces and extract what is coming from Ekman for each of them and look at every component. That should be possible. It's a lot of work, but it should be possible.
Well, generally, if you excluded average value, that you exclude wind component, I think. Is it possible to say that this is a density contribution to variability?
For the intrinsic part, will certainly not include the wind because the wind is atmospheric very fast.
Yeah.
That's for sure.
So is it the density contribution?
So it is certainly, it is basically it's the eddies. But the thing is, it is, if we have no eddies, all the intrinsic is zero. So the eddies are contributing, but we don't know what type of modes. It could be that small-scale eddies excite large-scale modes. And what we see are the large-scale modes, but those large-scale modes cannot be excited if we don't have the
So
eddies.
it's plus non-linear contribution.
Yeah, it's a, yeah, well, I would call it this way, the non-linear contribution. Yeah, exactly. More than, that's why I mentioned the coarse resolution model that doesn't resolve eddies as laminar. I think it's a proper way to say they are laminar than coarse resolution, which don't know exactly what it means. So laminar flow and turbulent flow. Yeah. And non-linear flow. So that's it. So now get to the mega grant, you know, with the ocean modeling laboratory. I will tackle some issues. So the issues, the objective is to so it's an ambitious project, but I'm not sure. I don't think we're going to solve fully the problem, but we're going to make a contribution to the problem of understanding the role of the synoptic and mesoscale eddies in the large-scale oceanic circulation at global and regional scale, and their role in the climate variability. So that's we want to work on these things. And to develop a modeling approach, the idea is that we all the modeling expertise that we develop in the group in Grenoble could be beneficial to the Cherchov institution, and we want to strengthen the modeling capability of this of the Cherchov institution. But of course, you know, the Cherchov is very good and very important in observation for the ocean. So that is also included in the project. So the modeling approach through regional high-resolution modeling to look at the scale interaction, because you cannot tackle the climate variability without scale interaction, and the role of the mesoscale on the large scale, this scale interaction. But because the ocean is turbulent, of course, intrinsic and force variability must be investigated. And also, we intend the modeling approach that will be in cooperation with the MGO laboratory in St. Petersburg, that the component of the Earth system model in St. Petersburg will be an eddy permitting model. So at least part of the variability, the one that have been shown in the 1/4 degree model, could feed back in the climate system. We also have a focus on key areas which are linked to the IOS observational activities. The northern North Atlantic and the Arctic, where in the northern Atlantic there are repeat sections every year. We're looking at regional seas, and especially in the Black Sea. And of course, the global ocean. I mean, if you tackle climate issue, at some time you have to go with the global ocean. So these are basically the, and I will have certainly more opportunities to talk about that in the future. But what's very clear is that large always will require intensive computation and big computer power. Thank you.
Thank you, Bernard. Questions, please.
Okay, so may I start? So you told that when you increase the resolution of global ocean model, you get this long-term variability in the ocean that you lack in the coarse resolution simulation. Maybe I skipped, but what is your explanation or some idea of what is the mechanism that makes this variabilities higher?
So I think there are several mechanisms. One of them is, and I think that concerns not the too long scale, you have, when you start to generate eddies, okay? When you do those eddies, they appear in one place, they disappear, they live a year or two, and things. So when you do some averaging or some filtering, you may have still a signature of those eddies, because maybe to filter out the signature of a mesoscale eddy, you need 10 years of averaging or filtering. So at a scale like 2 years, 3 years, it could be a residual things from the eddies. But, so that's one thing. Signal, so that would mean that the signal, this type of signal is probably not important for climate. It's just a single structure that lives long and move around, and another that appears. And when you do some kind of filtering, you have traces of them. You don't remove them, and you should remove this partially. But that is not the dominant signal, because we looked also, we have been doing some large-scale spatial averaging, and the same appears very strong. So what we see, I can go back to this. Is when I show the I think large part of the signal is waves. Okay. Okay. So this is the shape of the intrinsic signal. If you look at it, you can see, those band-like structures. Okay. Propagating westward. So those are probably Barnier Crosby mode. Okay. And they are probably generated by the eddies are shaking the system by their presence, and when you shake a mode that can be resonant, the mode just take this energy. It's like some kind of noise to excite a large scale mode. Okay, so that's probably one of the aspects. In that region, it's probably more complicated because what we've seen, like you see, in all this, we've been looking at temperature. Upper ocean temperature, the low frequency molecule is run, and we found that we have anomalies of plus or minus 2 degrees that persist for 5 or 6 years. Of a large area like this one. But we haven't put the finger of what type of, how this thing is changing. So there are, in fact, that's the main task that Thierry Penleuf is working on now is to identify the generation mechanism and what type of mode and things like this is doing. But at the moment, so for sure there will be Rossby waves, low frequency wave. We found that we get variability up in this simulation up to 15 to 20 years. So very, very low, slow modes that exist and are present. But those modes could come from mode interactions. Because the non-linearities, when you resolve non-linearities, then you can have mode interaction, and that makes the system more complicated.
I missed how do you construct the seasonal forcing?
Okay, so this,
you extract the internal modes, but
we do some filtering to extract the internal. In fact, we do a climatology. Okay, here you have 50 years. Okay, of 6-hour forcing. So you average every 1st January and 2nd January. You do some of climate over the whole 50 years. So it's a kind of averaging we do. Well, this is described in this paper, I think, 2011. I can forward it if you want. The important thing in making those two is that the wind, high frequency wind, inject a lot of energy in the ocean. And when you drive an ocean model with a seasonal climatological wind, you're losing that part. So there is a part that you lose, which is a non-linear contribution in the Doyle formula. And for that, we work out a correction on the wind forcing. And to test it, we've been running, calculating the amount of energy that we put in the two model and looking at the trends in the simulation. And we found that the surface forcing were very, very, very close to each other in the two experiments. So that's been done. So this is described in this type of paper. But it's a tricky one. You're doing climatology just an averaging, but then the response of a model with the climatology 30% less energy than with a full forcing with high frequency winds. So you need to compensate for that.
So you get like a spectral correction.
Yeah, well, what we did is that the wind forcing, the wind stress is U squared. U star is the square of the wind velocity. So we also calculated the climatology of the high frequency of the momentum input. So I can.
It looks that edges in ACC are induced by topography. Is it true or not?
It's partly, not all, a significant amount of the eddies results from topographic constraint. It's true, but not only. There are, so you have also eddies generated by baroclic instabilities and.
I suspect if you use flat bottom in ACC, it would be they disappear completely.
No. I think you will get eddies. You will get. The thing is, what you will get an ACC which will be 200 or 250 Svedrup, large shear, and
I mean, shape of edges would be other.
Yeah, but we will change stratification. You'll change your.
Will be approximately right.
Because it's associated with topography.
Questions, please.
No, the thing is, you know, this path, the path of the ACC this way is always force. So the force push. That's what is pushed to the poleward by the colorless force. That's it. So that's why the ACC is not going straight this way. The drag passage is set.
Kerguelen plateau also without edges, for example.
Yeah, it's true. But but in the 112 degree model, when we increase resolution, we get those eddies. So those eddies, we don't resolve them at 1/4 degree, what they are present here. And in the 112 degree, we do get them.
More questions, please.
I have one more question. So we were talking many things about increasing resolution. So it may make an impression that increasing resolution will solve all the problems of ocean modeling. So I would say that I missed.
Didn't we solve all
Okay. So that's. But I missed maybe some speculation on how physical parameterization should change with changing resolution.
So that's a very important question. Getting there. This model, the subcase parameterization are exactly the same as the one we used for the 112 degree model. And we are convinced that it's the wrong thing to do. That we should have a different one. Okay? But at the moment, the subscale parameterization for such model hasn't been developed, and we cannot investigate this subscale parameterization for such a model with a model that costs 70 million hours. Okay? This needs to be an approach with more regional model, and this work has to be done. It's also the same issue for the numerical schemes. What I didn't say here is we started with a numerical scheme which conserve energy for a momentum advection, which conserve energy and entropy. And that model, where the eddy kinetic energies as model was less than the one we had with the 112 degree model. We changed the advection scheme of momentum, and we obtained eddy kinetic energies that is very comparable to observation, and significantly higher than the 112 resolution. And that we discovered that the numerical scheme we were using had some instability that was basically destroying the mesoscale, the eddy field, damping the eddy field, but only when we had a very high vertical resolution. And it was the first time that we were using 300 levels. And that was, so the numerical scheme also has to be revised. So that's why I think it's a big challenge, modeling and computing challenge, because now we are entering this type of simulation. We have to think about the numerical scheme we're using. Are they the proper one for that type of resolution and that type of physics? And this has to be revised. We need to work on that. So some people are working on this in Barnier, in Grenoble, in the applied mathematics department at IMAG. We are working, we're working at the moment from the fourth order vertical erection scheme. There are things to be done. There are also the sidewall boundary layers. Things as simple as that. Your vertical wall, what's the friction, the load at the wall is not the same when you have a grid of 100 kilometers and when you have 800 meters. So that's a very critical issue, and we are just discovering those issues. But hopefully we are not the only one to discover. There are some few groups are doing this type of simulation. And we might learn eventually from computational solutions, which are very high resolution and small scale. We might learn from them too.
In addition to the previous question, did you use giant Macmillan's parameterization in this configuration? Or not?
No, we don't do that when we are with this. We only use it in the 2-degree model, in the coarse resolution laminar model.
So it's not using quarter degree resolution and final.
No, not even in the quarter degree. We let the AD do the job, which poses problems at high latitude. Because when we don't resolve ADs, we should have some parameterization of the ADs. That's a problem of the quarter degree resolution, which is resolve ADs on part of the domain and doesn't resolve ADs on the other part. So we should have a parameterization that switch. There have been attempts to have such a parameterization that switching from J. Macmillan-like to no things, but none of them has been working.
And what about 1 degree resolution model? Should we use this parameterization?
Yes, I think you should. Well, 1 degree you should use it. Even at half a degree, I think you should use it. Starting with a quarter degree, there is a debate.
I know quarter degree is not
and that you have different point of view. There are different point of views from the quarter degree.
Any more questions, please?
I'm sorry, I have non-scientific question. For one of project, you have used acronym like
Occiput.
What does mean in, let us say, in French language?
Well, it's a bone in the head. Something like that. There's a bone, crazy scientist.
Questions, please?